If you couldn't already tell what that brilliant artwork showed beforehand, starting off with this explanation of nuclear propulsion, we need to find out what nuclear really means. Which it's just the process of nuclear fusion or fission to produce electricity. I'm just going to give you a quick rundown of the two, but I'll pay more attention to fission because that's mainly what we're going to be focusing on. But nuclear fusion is when two molecules fuse together to release energy. Simple. Typically, two hydrogen ions are put under mass amounts of pressure to overcome the forces holding them apart, hence fusing them to create helium. It is this same ability that powers the sun.
Wow!
Nuclear fission is the process that splits molecules using impact of another particle to create energy. Typically, the particles have to be slowed down when split to continue a domino effect. Fission is a cheaper way to create power than fusion. These fission reactors use uranium to create a mass amount of power. When uranium splits, it releases a neutron to create radiation and to split other molecules, causing a chain reaction to go off to other molecules to cause them to split, to cause those molecules to split, and so on and so forth. To create a reactor, it starts out as the core, and inside the core there are many rods placed called control rods. Not only are they used to hold hundreds of pellets of uranium, but they also do the job of containing the reaction inside the core. Each of these pellets has the same energy as a ton of coal. The water then comes from a pump to the core to create steam. This radiation heats the surrounding water, which has the application of slowing down the neutrons, and in different areas used as a coolant to balance the temperature. The steam is then transferred to a turbine, resulting in electricity. The leftovers are used again to go right back through the system. Despite the many complaints of reactors and the events that have happened through nuclear energy, it is one of the safest ways to produce power. If it is kept in correctly and monitored, you should not have any unstable overheating problems with the uranium. But what if we could get rid of the uranium altogether and use a different element? Thorium is a lot like uranium, except he doesn't really suck. Uranium, when mined, does not only produces cancerous gases, but is also extremely rare. Thorium does not have any cancerous reactions, and there's 3 times more abundant than uranium. Something funny about uranium, it has to go through the enrichment process before heading to the reactor, so there's just so much more time wasted. Thorium just goes on ahead, except he needs something else to help him out. This may sound awful at first, but it's essentially a failsafe. When something fishy happens, or your element gets heated up, you can just move thorium away from its new friend and make him depressed, so he does nothing. So the reaction just stops. People are still concerned about whether we should use thorium reactors instead for a few reasons. One of them is the cost of converting all of our uranium reactors to thorium. The only other problem being that people are just scared of new things. Why do we still use uranium in such a multitude? Well, there's one reason. Uranium is a key ingredient in making the mass weapon of destruction, known as the atomic bomb. America, like many other countries, creates an excuse for mining uranium for electricity, when probably almost half of it goes to making bombs.
Thank you, Josh, for that wonderful demonstration about how nuclear reactors work. Now, how the actual reactor works on a propulsion rocket is very similar. These reactors work by heating up liquid hydrogen, actually, instead of liquid like water or liquid salt like you would see in a thorium reactor. This diagram here shows us what this actually looks like. So you have right here, you've got the big container of liquid hydrogen that is going to be pumped around our fuel rods here, and the fuel is going to simultaneously cool down the fuel rods and be used to propel our rocket through space. Now, because we are in space, we have a poor radiation of heat. All of these elements are covered in these fins that are going to help us radiate heat off as efficiently as we can, so that we can use our liquid hydrogen mainly for moving our actual rocket, across the sky. Insert funny transition here of Josh being thrown. You got that, Josh?
Yep.
Awesome. So now we move our rocket across the sky. Back to how this actually works. This liquid hydrogen is going to get heated up by our uranium or thorium reactor to somewhere around 2,500 degrees Celsius, and it's going to take that liquid to a gas. And now hydrogen expands a lot when it becomes a gas. Insert actual numbers here. I'll record this later. So the expansion is an insane amount, and we're going to force it through this itty bitty tiny nozzle right here. And this nozzle, it's going to increase the pressure that hydrogen makes to move it out the back of the rocket really, really fast. And this, in turn, using Newton's third law of equal and opposite reactions, this in turn is going to move our rocket forward at a speed similar. It is estimated that we can get speeds at insert percentage of light speed here, probably in the video using a visual. So as this is being propelled, we're generating more and more and more heat, which is why we have all these fins. These fins are going to help radiate everything off. Now, the really cool thing is the design is this is not 100% efficient. A lot of these gases actually get recondensed back into hydrogen and get put back into liquid hydrogen and get put back in the tank, only for them to be pumped through again. So this design actually uses essentially a rebreather, or like how your car on a turbo will funnel your exhaust gases through the turbocharger to put it back into your engine. A rebreather does the same thing. It takes the air and it cleans it and it puts it back into your body. It reoxygenates everything, and it's like, yeah, go, you breathe. So the major components of this, you've got your reservoir, you've got your pump, your reactor, and your nozzle. Those are all that you need to make this go very fast. However, you cannot use these at all in Earth's atmosphere. They generate too much heat. There's too much risk. So these would be used in a dual stage rocket. You would have a chemical stage or maybe electromagnetic stage that'll take you from Earth into orbit and out of Earth's gravity and atmosphere, so that our radiation goes better with our heat. And then you can start using the actual nuclear propulsion device to get yourself out there. It's a lot of pretty interesting stuff. I'm going to now turn this over to Jarrett Linden for some facts and some history about this stuff.
Nuclear propulsion has a very interesting history. One of the most basic of these ideas dates back to 1940 with the simple idea of by dropping nuclear explosive charges out the back of the spaceship and riding the blast waves. This was later attempted in 1960 on small scale through various experiments, but was unable to be completed due to a nuclear test treaty of 1963. It had some pros and had some cons. One of the pros was that the proposed max speed of the project could be 15 to 20% the speed of light, which of course was never achieved, but it offered an interesting solution to the rocket fuel power problem. The basics of Project Orion include literally throwing a massive nuclear weapon out the back of a spaceship, detonating it, and hoping that you can catch the blast just right to where it propels you through space at a ridiculous velocity, instead of turning you to ash. One of the interesting side effects of this was during testing, scientists may have accidentally created the first man-made object in space when they detonated a low-yield atomic weapon below ground in a mine shaft. The nuclear weapon turned out to have 50,000 times the calculated amount of power, and may have launched a 2,000-pound steel manhole cover into space at 6 times exit velocity, going so fast that it would actually melt in the atmosphere. Later, scientists, after doing the math, realized that this was possible and fixed a super high-speed camera, pointed at the manhole cover and launched it again, the manhole cover only showed up for a single frame of the video.
One hop this time. One hop this time. Right foot, 2 stumps. Left foot, 2 stumps. Crisscross. Cha-cha real smooth.